So we have started the Ampere circuit law. So yesterday was JEE Advanced. Did you see the papers?
Oh, sir, I have to check it, sir.
You have paper?
Sir, no, sir. Sir, you have the PDF? I mean, will it be like immediately sent out, sir?
Just a minute. Okay. I have sent it anyway. So most of the questions like we had discussed in lecture, nothing beyond that. So for the
Okay, sir.
topics that we have studied, everything was much within the syllabus of JEE, and also all questions like were discussed with values differently. Okay, those different.
Well,
So Ampere circuit law.
sir, how was the paper? Like
It was
easy
easy.
or
No,
medium
no.
or difficult?
As per the expert, it was difficult. Yeah, it was difficult for many. But if you have studied my notes, I won't say it's difficult. So
Okay.
you can go through the paper, you can see for yourself, and you will tell me the right feedback that how much you studied and what kind of question which they appear there, how difficult are they. So as a
Yes.
teacher, it's very difficult because for us it's like we remember everything. So for us it's everything easy only. So we don't see the difficulty. Only student can tell the difficulty.
Yes, sir.
Yeah. So we are not the right person to tell.
Okay, sir.
So we saw the magnetic field due to the current carrying wire, infinite wire, and we took two scenarios. One in which the current is uniformly distributed over the surface, and the other scenario was when the current is distribution is varying over the cross section. Okay. So like I gave you J equals to J not 1 minus R by R. It could be any formula, and accordingly you would have got the answer. Okay.
Yes, sir.
So now we'll go for the calculation of B. Due to infinite solenoid, so if we have infinite solenoid, then the B is going to be uniform. And infinite means the length is much bigger than the cross section. So we can say the axis of the solenoid and the entire volume of the solenoid are close to each other. In a way, there is a volume around the axis, right?
Yes, sir.
Okay. So now having this axis of solenoid, so this is the axis of a solenoid, and so we can say that okay, we have the current wire going like this. Okay. This is the cross-sectional view of the wires. So we have a cross. So we have dot and cross, as you can see. This cross is not visible. So now what happens? It will create a uniform magnetic field, as we know, inside its volume. So the inner part of the volume will have uniform field. And because of the taken direction, I can see this will be on the left. But as you go outside, the field will have the curvature, so it will go like this. And some of the field will be like this also. So we'll not show that part. Now what we need to realize that the field just outside the surface is always zero. So the B here is always zero. I'm saying just outside, not far away. And that is a property of any bar magnet as well. So if you have a bar magnet, and if we have the north and the south pole, then exactly at the center is called the null point. And null point is a place where you won't get any magnetic field. Okay.
Okay, sir. So like exactly just after the surface.
Yeah, just after surface. The reason is if you go away from surface, then that if let's say if you're here, then north will repel and south will attract. So net force will be like this.
Yes, sir.
So only near the surface, because if you are here, then there is no field lines which passes through the surface actually. All field lines will go like this.
Yes, sir.
So you won't get anything something like this. That's the reason.
Theoretically not possible.
So we can prove it through some manipulation. So to understand the concept, let's take two adjacent cross section of the wire.
Okay, sir.
This I'll draw slightly ahead. Let me draw far apart as of now, just for understanding. And these are the top one, the cross one. And similarly, we will have the dot also. We'll show it later. Now, for any small piece of conductor, if you have take a small piece of conductor, even though it is wrapped around the cylinder, can we say that a small piece is a straight wire of length DL? So we can
Yes,
say
sir.
yes, DL will act as a straight wire, and therefore, if you go very close to the wire, if you draw a circle very close to the wire, it will be a perfect circle. Like.
Yes, sir.
So around the straight connector, the field lines will be circular, isn't it?
Yes, sir.
Now we'll extend it just for the understanding part. And this is the field lines made by the first wire, the left wire. Similarly, the right will also make the similar thing. Correct. So
Yes, sir.
these are the two adjacent wires, and these are the two circles, or you can say field lines, which they make independently. Now, if I make the two wire very close, these two circles will almost overlap, isn't it?
Yes, sir.
So technically, that is something that you need to just remember, but the rest is. Now we know that the field lines will be clockwise.
Yes, sir.
So at this point, which is the point of intersection, if we try to draw the field lines of each wire, one will be tangential to the point here like this, another is like this. Correct?
Yes, sir.
And similarly, we can say one is like this and other will be like this. Okay.
Yes, sir.
And if I call just like a B and B, and if I also call B and B, we can clearly see something that the resultant of the two will be like horizontal. Okay. So this will be symmetrical, and we can say this is 2b cos theta. And the same you can say for this here also. So now you can see that we have a magnetic field, and the direction of magnetic field just above the wire. I mean, see, we are only discussing just above the solenoid. So just above the wire is going to be the right side and left side, right?
Yes, sir.
So for wire, the if you look at this portion of the wire, the field lines will be of course cylindrical, but near the surface at this location it is like this.
Yes, sir.
And at the same time, just below it is okay, already shown. This is like this, which means a top layer will create a field right above and left below, which means everywhere it is left, including the bottom also. So just above the or outside the solenoid, the same field direction we can also assume here. Okay. So right, left, left. It is clear so far.
Yes, sir.
Now, if we analyze the bottom, which is the dot, it will have the reverse property. It will create left up above and right below. Just imagine the
Yes,
dot instead of cross. What will happen? So it will create a the dot will create a left above. It means it will have left everywhere and right below. So that is the realization point that just above the surface, the pairwise cancellation will make the net field 0. But inside the volume, they will add up. And this we are saying for one particular plane. So if you draw all the possible plane, you get the similar answer. And therefore, we say that in case of magnetic field due to infinite solenoid, we never talk about the finite one. Due to infinite solenoid, the answer is always 0 just outside the solenoid, and it is non-zero inside the solenoid as well as it is uniform. Now,
yes, sir.
once we understand that, okay, this is the field lines, and because we are trying to understand the B inside the solenoid, the logical imperial loop that we need to draw here, this is something which you need to learn actually. So we always draw a loop which will at least have the parallel side with the B actually. So we make sure that one of the side is parallel to the B. You can draw something like this. So once you draw something like this, in which a part is outside, a part is inside, this kind of loop will have the benefit that it can have at least one side which is parallel to the B, And other side which I have drawn, I have taken it at the right angle so that the B dot DL, we know that B dot DL will be 0 if it is at the right angle, and B dot DL is also 0 if it is at if there is no magnetic field at all present. So which means if I name it A, B, C, D, and because the current is cross, so I'll move clockwise only. That's easy for me.
Yes, sir.
Then the B dot DL, which we generally write, which we like tracing the B along the path, closed path or contour, is mu naught into I enclosed. So the loop means the B dot DL should be iterated over the entire loop from A to B. Then you will again iterate from B to C. You will do it for C to D and D to A. And this is equals to mu naught into I enclosed. Okay.
Okay, sir.
Now we can evaluate each term one by one. So A to B is 0 because there is no B actually. So from A to B, we don't have B actually, right?
Yes, sir.
So this is since B itself is absent, so this entire term will be 0. Okay. From B to C, it is also 0 because here the angle is theta is 90 and absent also. So for some part it is 90, for some part it is absent, right?
Yes, sir.
So B is 0 also and theta is 90. So there are two reasons possibly which we can explain. Now C to D is
The
interesting.
B is 0. How?
This part is 0.
Only that part is 0.
Yeah, and this part is non-zero.
Yes, sir.
But although it is non-zero, the B and the DL are mutually perpendicular.
Yes, sir.
So this part is 0 because of two possible reasons. From C to D, the good thing is the B and the entire length is parallel. So if I call this length as L, this will become B into L because B dot DL is BL, right?
Yes, sir.
And the D to A is again 0.
Yes, sir.
For the same reason, some part is 0 and some part is 90. Okay. And now comes the current part, I enclosed. So I enclosed is like what crosses the contour part. That's called I enclosed, right?
Yes, sir.
So how much current will cross this contour? So N is the number of turns per unit length. So NL is the total turns, and every turn will have I current. So this
Yes,
is your current enclosed, right?
Yes.
And therefore now we have answered BL equals to mu naught into NI into L, and therefore L gets cancelled. What you get is B equals to mu naught NI. This is what we derived, right?
Yes, sir.
So similar logic we can apply to derive other formula if we have a charge drum. And if I call this as infinite drum, and if it is rotating, instead of going through the derivation or comparing the solenoid, you can directly derive by calculating the current through the contour which you can create. Okay. So in case of charge drum, it's easy actually because you can find easily how much current will cross this drum, this cross section during rotation. So that will be equal to the charge present on the curved surface of this cylinder up to L length, right?
Yes, sir.
So that is what you can always do. You can choose other symbol L dash or something because if it is confusing, if L is the length of cylinder, you can choose something X or whatever you want. So, okay, the final answer is B equals to mu naught Ni, and of course, this is only true for the infinite solenoid. It means when the points are considered far away from the edges. So only true when the point considered are far from edges.
Yes, sir.
Okay. Next. So after the infinite solenoid concept, we can go to the next derivation that is called toroid. So toroid is a donut shaped tube, and the so toroid is a donut shaped tube, and you can think that it is made like if you take a infinite solenoid, and if you join the solenoid end to end, what you get is a shape called toroid. So the basically the toroid was designed by a Japanese scientist called Tokamak, and it is also called the Tokamak design. And the primary goal was to create the fourth state of matter, to create fourth state of matter that we call plasma. So plasma is a state of matter in which the atom do not exist, rather the nucleus and the charges exist together. So there is no concept of atom in the plasma state. It's a very high temperature state, and because the temperature is so high, which is you can think of the temperature to be more than temperature of the sun surface. Now, at that temperature, I mean, we cannot have a vessel which can keep that object, right? Because that temperature is too high.
Yes,
So
sir.
anything which will cross that temperature will lose its identity. It means, I mean, we cannot create a vessel to keep the plasma. So Tokamak said, okay, let's design a toroid. And what they did was, using the magnetic field, they were able to float the plasma inside the toroid forever. So the magnetic field will keep it afloat all the time, and therefore it will not touch any boundary. So you can imagine a tiny piece of plasma, as small as a micrometer uh, dimensional plasma size in terms of volume. So that small plasma can be floated in a big a meter size toroid in terms of radius. And therefore the although the temperature is very high of the plasma, but because it is not even not remotely close to the wall, it will not affect, or the temperature will decay very drastically as it will go away from the plasma location, and therefore while reaching the wall of the toroid, it will not damage it. So that was the whole idea, that can we create the fourth state of matter and still keep it afloat in a vacuum so that nothing it can conduct. So we were trying to prevent the conduction of the heat, because that is going to be very destructive. That heat is quite dangerous. The same thing is with the sun. Sun is so hot, still it is so far. It is so far from the earth that the temperature falls drastically. Even the energy that we receive will not destroy the earth directly, although it is very destructive even at such a astronomical distance. But the good thing is earth will have the magnetic field, and the magnetic field is so powerful that most of the cosmic energy is actually captured by the magnetic field layer of the earth, and a very tiny part only received by the earth's surface, and still we are surviving. So imagine how powerful are the rays that even astronomical distance away it can create havoc, although we are
Yes.
receiving a very tiny part of it. So we are receiving a very small part of the sun's radiation, and still it is so powerful and dangerous. So that's why the design of the plasma, I mean, sorry, the tokamak design, the toroid, was essentially meant for this. Now the toroid shape object is the basis of called particle accelerator. So in CERN lab, you can say CERN is the center, European Center for Nuclear Research. It is called CERN, but it is read as European Center for Nuclear Research. It's very different way of reading. So it's English name, but that's a French or something. They some of the European language. So in the CERN lab, they have designed roughly 27-kilometer perimeter toroid inside the Earth. Okay, so that's the biggest, you can say, tunnel on Earth, and now they are creating 100-kilometer perimeters toroid. That's the biggest, you can say, ambitious project in the world, you can say. And Sun is responsible for development of a lot of technological advancement in the world. And you will be surprised to know that the entire internet was developed just to communicate among the people of CERN, because thousands of scientists work in CERN, and because it's a perimeter is 27 kilometers, so everyone is located at different points on the perimeter, and they do some research, they do some lab work. So what they did was they tried to create a intra communication network, and that resulted into something called intranet. Later on, the thought of providing this to the entire world through the same logic, and that's how the birth of internet took place. So that's a biggest revolution, you can say, which changed the entire world. The world in which we live today was designed at CERN. You can say that.
Yes, sir.
Every year, thousands of engineers join CERN. Most of the PhD students are postdoc into astrology, or you can say advanced high energy physics, or various subject related to physics. They join CERN, and they work there. So you
So
can
your
also do.
voice is scratching.
Am
Hello,
audible
sir.
now? Am audible now?
Sir, just a second, sir. I'll just change my internet. Sir, able to hear me?
Yeah, I can hear you. Can you hear me?
Yes, sir. Yes, sir. So for like 2-3 seconds there, your voice was breaking.
Okay, so I was just saying the same, that the whole purpose of toroid is to create again a magnetic field. Okay, and that magnetic field will keep the moving charge afloat. Okay, so we know that later on we'll read actually or study that moving charge experiences force due to the magnetic field, and we keep it afloat inside the volume. Okay. Also, the concept of magnetic levitation, which is like on which the far you can say the maglev train runs. The maglev is a short for magnetic levitation, in which we create the bullet trains. So bullet trains are run on a track inside a tube actually, and in that tube, basically you can imagine the entire train is like a solenoid inside a big tube. So the solenoid itself is a source of magnetic field. So solenoid creates the magnetic field, and that magnetic field will interact with the other magnetic field of the toroid kind of shape, a big tube shape. And because of the repulsion of the two, you can say two solenoids, you can say this way, that will be, you know, kind of floated in air. So because they cannot touch each other, and the floating will create the zero resistance. And because the tube is vacuum, so it is like almost neither drag nor any physical contact. So there is no resistance, almost zero resistance. So you can achieve a tremendous velocity. Okay.
Yes.
The only restriction is that at high speed, the stress developed in the object is very high. Okay. And it is not just the straight path, because the tube will also turn. So it will create a tremendous centripetal force. Okay. So we make sure that the centripetal force is not high enough to break the structure. Okay. Because on which you are building something on a physical object, and it is, kind of mounted on earth. So it is quite possible that at very high speed, when you turn, it will create such a high, tremendous centripetal force that it may break the structure. So the stress, or the, you can say, the wear and tear is taken care, and that is how we achieve the very high speed. So in future, now we are going to create the hyperloop, and the hyperloop will create the most effective magnetic levitation, in which the speed attained will be more than the flight speed. So imagine that you will be almost on the ground traveling at a speed more than the speed of the flight. So you can travel even large distances in very small time. So maybe the time taken to go from the London to New York will reduce in hours.
Yes,
So
sir.
that is the,
Sir, but we
yeah.
need the means of going there.
Yeah, no, but yeah, of course, those loops are created. It is underwater, in air, everywhere.
Yes, sir.
Yeah, that's the future of travel. I mean, you will hear about this more often. Maybe after 10 years, you will see the realization part. So the infrastructure is still in the process of making. Dubai is going to first implement the Hyperloop.
Yes.
So most cities of Dubai, let's say, if you want to go from the farthest, let's say from Oman to Abu Dhabi. Okay, I don't know how much time right now it will take, but if it is 1,000 kilometers, you can expect roughly 1 hour.
Wow.
So 1,000 kilometers 1 hour. So you can see that the kind of transportation will bring the huge change in the way people live. So
Yes, sir.
there is no need to live near the office. You can live 1,000 kilometers away and still access your office in a very due time.
Yes, sir.
So that will be really nice. Like people who are having settled in some location, and they got a very high paying job in some remote location or very far location, they will not bother about the location. They will just travel there, will they do their job, and will come back their home. So that's kind of infra we will have in future, and thanks to all the technological advancement. Okay, so the
Yes.
hyperloop, the future of travel.
Yes, sir.
So now, how we design the toroid? So as I said, it is simply, you can think as a solenoid is bent in a donut shape. So you just take a solenoid and join the ends, you will get this kind of shape. Okay. So now you can wrap up the wires. So you can see a large number of turns of wire is wrapped. Again, see, number of turns here is fixed. That's called N is the total number of turns. You can clearly see the turns are closer on the inner surface, isn't it?
Yes, sir.
But the same turns are slightly farther on the outer surface. Although the gap is not much, but there is a apparent separation that we can understand. And because of this reason, because the turns are getting farther apart as you move from the inner surface to the outer surface, one thing that we can understand is is what?
The magnetic field is not that uniform.
Correct. So it will not be uniform. It will be circular, because if you take a solenoid and if you bend, all the field lines will turn. But as they turn, they will become non-uniform. So the field lines that we can expect here will be closer near the inner surface.
Yes, sir.
But as you go away, the separation will grow in value. Let me draw just few one, not much. So a toroid is known for creating the non-uniform but circular magnetic field. Okay. So assuming the direction of current is this way, if the current is entering this way, so the field lines will be, you can see this will field lines will be like this. And if this is the direction of field lines, like this. Okay.
Yes, sir.
So now if you want to know the, if you do a cross-sectional view, so cut like this, just to mention the cross-section. Then current is, you can see current is entering from the inner side. Okay, I'm just drawing a bigger one just to reduce my effort, nothing else.
Yes, sir.
So this is something like just for people. This is too much. Okay. Anyway, this is really bad, but anyway. So the current is entering like this,
Yes, sir.
and it is coming out of this, right? It's a huge dot. Huh? Anyway, so somehow I finish this drawing with my effort. So current is entering and it is leaving the from outer. So what you will see is the in and out only. This is the cross-sectional view. If you cut it horizontally, you will get this view. And the field lines is like this. Okay, so our field line is circular. So the imperial loop must be parallel to the field line. So it means the field line must be circular itself. Sorry, the imperial loop must be circular itself, right?
Yes, sir.
Because if you have these lines, then definitely the B dot DL is going to be really simple.
Yes, sir.
So, okay, let me write on the next page. So if I choose the radius to be R, and if this is my imperial loop, the B and DL are going to be parallel.
Yes, sir.
So B dot DL becomes B into 2 pi R.
Yes, sir.
So B into 2 pi R equals to mu naught into I enclosed. I can see that since all the n turns are within this loop itself, everyone is passing through the loop for sure. So the total current is passing through it, isn't it?
Yes, sir.
And since each turn is giving you I current, so the total turn is N. So we have N I current. Okay.
Yes, sir.
So you can see the B turns out to be very simple formula, mu naught capital N I upon 2 pi R.
Yes, sir.
So for toroid, the way to remember is it is mu naught I by 2 pi R. Now, is it necessary that the toroid must be circular? The answer is no. A toroid can have, sorry, circular means, is it necessary to have the cross section of toroid circular? The answer is no. A toroid cross section can have any shape. It can be rectangular, it can be hexagonal, it can be any shape, but the cross section should be uniform. That is the first rule. And the second is the field lines, as long as the overall shape is circular, the field lines are going to be circular. Okay. So you will come across a toroid with different types of cross section. Is this clear?
Yes, sir.
So after toroid, yeah, you want to say something?
Sir, the cross section must be uniform in the sense.
In sense, as you walk along the tube length, let's say if you walk like this, so it should not get narrowed. Like if I have a tube like this, and again a narrow here. So this kind of toroid we don't expect
Yes, sir.
because here the cross section is different. No?
Yes, sir.
So let's say the cross section is not like this; it is like this. So even a rectangular cross section is also okay.
Okay, sir.
Understood.
Yes, sir.
The only criteria is that the cross sectional area should not change. So you can see this area is different from this area. No?
Yes, sir.
So this is the like variable cross sectional area. So that is what's something which we don't want.
Okay, sir.
And these all formulas you are going to use again in the next chapter, because you have to use the same object, and you will be calculating the flux. Okay. And with the help of flux, you will find the answer.
Yes, sir.
All right. So after toroid, we have something called the infinite current carrying sheet.
Sir, can you just come back in a minute? Sir?
Yes, yes, you can go.
Sir,
Yeah, tell me.
sir, I'll just log in through another device. I'm currently attending through phone. My sister's
Okay, okay.
class just got over.
Yeah, sure. Go ahead.
Okay, sir.
Am I audible to you? Am I audible to you? Hello, hello, hello.
Sir?
Yeah, am I audible to you?
Yes, sir.
Okay.
So sorry for the delay.
So infinite current carrying a sheet. So we have a sheet which is carrying current and it is infinite in all sense. So so this means like it is stretchable in this direction. So all can go to infinity and current is moving fairly straight line and it is moving parallel to one of the side. And the thickness of the sheet is taken to be very, very small. Sorry. So now the current is moving parallel to the sheet, as you can see. The thickness of the sheet we take as very small. And we are going to take the flat sheet. It's not curvy as it looks like. And because the sheet is very thin, so we don't define the area, we define something called length. Okay, so here we define a new term because the sheet is infinite, so current is also going to be infinite. So we cannot say what is the current, we can just say it is infinite. So what we define is called J, but the J is not the regular current density which you studied. It is called the linear current density. Okay. So it is like if you take a small piece of sheet, look like this, of length dl, and let's say if you want to take thickness also t. Okay. So with your regular definition of current density, the current density I will add Js, which we define for the surface. So current density we define as the current per unit length, per unit area, which is dl into t. Correct?
Yes, sir.
But if you want to define JL, let's call JL. The JL you define as di upon dl only. So you can say that JL is basically Js into thickness. Understood?
Yes, sir.
So we define linear current density, which is defined as current per unit length of the cross section of a sheet. Like the length of cross section of sheet of unit length will have current of J value. Okay. So for solving problem, we don't call JL, we just call J. So from the context, you need to understand JL as J, and this should not create any ambiguity. Okay. So JL equals to J, and now what we'll do is simply cross-sectional view of the entire infinite sheet. So we don't do the entire sheet, just cross-sectional view. And you can see that this will go up to infinity on both sides. And what you're looking is the cross-sectional view. Always remember, right? For the sake of solving problem, let's call the current to be going into the plane. You can choose out of the plane also. So and this current, again, if you remember that we discussed something like that, the nature of field due to the state connector just above the surface, right?
Yes.
So this is if you take two wires one by one, so these are like infinite wire, and they will create the circular magnetic field lines individually, right?
Yes.
Every wire will create a. So if you look at a one circle, it is like infinite wire going into the plane, right?
Yes.
And around that wire we have going to have circular loop, right? So the net field that you get above will be right side. So the B will be parallel to the surface. That is the property. So B is going to be
Yes.
parallel to surface on both sides. On both sides. Okay, so this is the B direction, which means current carrying sheet creates a uniform and parallel field on both sides, and the direction we can easily understand it. If it is crossed, then up right and left down, down left. Okay,
Yes.
and therefore it is imperative to draw the Ampere loop which is parallel to both of your desirable length, and then the B dot dl, which you write is mu naught into I enclosed, will become 2bl, right? If I move like this, so the B and L are parallel on top and bottom, and for the vertical there is no B dot dl is 0, right?
Yes.
Isn't it? So this will become 2bl, convert 2bl, and the current enclosed will be how much in terms of J? So J is the current per unit length of cross section. So for L length, how much current it will enclose?
J.
J. And so you can see L gets cancelled. So B turns out to be mu naught J by. So this is what you need to remember. The linear condensity, it is current per unit length, and B becomes mu naught J by. Is this clear?
Yes.
So these are the various types of field that you need to know. And you will get a question like if you have multiple infinite sheets kept parallel to each other. It's a very common question. So all are infinite sheets. And what you're looking is the cross-sectional view only. And if this is a cross dot dot J1, J2, J3. So these three layer will divide into four space, right? 1, 2, 3, and 4. So the magnetic field at the layer 1 will be so one by one. So at 1, the first will create right,
Yes.
and the second will also create left. Second will create left actually.
Yes.
Third will get left.
Yes.
So you can choose right as positive, then left will be negative, and vice versa. So the B at 1 will be the B net At 1 will be B1 minus B2 minus B3, right?
Yes, sir.
And I'm taking the right. And the formula will be mu naught by 2, and I can add J1 minus J2 minus J3. Okay. Similarly, you can do it for 2 or 3 and 4. Okay.
Yes, sir.
And I'll take a break of 10 to 12 minutes to have my lunch. Then I'll come back. Okay.
Okay, sir.
So now for 2, are you there?
Yes, sir.
So for second sheet, for second location, the point number 2, J1 will create left because it's below,
All
but
will be there.
yeah, and J2 and J3 will anyway create left.
Yes.
So the B net here will be all left. We can just add 1 plus 2 plus 3, and we can say the direction is left. Okay, so it is J1 plus J2 plus J3. Same, you can do it for 3 and 4. So this part we can do. So what we need to realize, this formula is similar to the electrostatic formula. If you remember, the answer was sigma by 2 optional, right?
Yes, sir.
Now sigma will become J here, and 2 will become 2, and 1 by epsilon naught becomes mu naught. So it's easy to remember in case if you just tend to forget. Think as an infinite sheet, and there is always correlation between the electrostatic and magnetic in terms of formula and derivation. Okay. So you can always do the same.
Yes.
Okay. So what next? I think we are done with the first part of magnetism. Let's start the next part. Yeah, so we're done with the first part.
So first part means the moving charges of magnetism part.
Yeah, no, first part means like the development of magnetic field due to the current carrying wires or the moving charge, you can say, like how the magnetism is developed. So we are able to understand that in various situations how we can develop the magnetic field. That is the first part, and this part is the most you can say important part from the point of view of electromagnetic induction, because in most of the cases the difficulty that you will face is in finding the field first, and once you have the field then you can do the rest of the job, which is not difficult. Okay, so next part is called force on a moving charge particle. Force on a moving charge particle kept in external field. So we know that every moving charge will create its own field, right? So the moving charge is the source of field itself, but the one who creates the field will never experience the force due to its own field, right?
Yes.
So self force exerting bodies are not possible. So we cannot have a charge which creates a field and applies force on itself. That's not possible. So who really applies the force is someone who is external to the experiencer. So if charge is the experiencer, then the field must be created by either any other charge or any other current carrying wire or any other source which we don't see. So the simple rule is force on a moving charge particle kept in external field means the source of the field is different from the charge itself. Okay, so I can say that is the source of field is different. The source of field is different from the charge itself. So this is the idea that we need to understand always. And under this topic, we are going to deal with variety of fields. So I'll tell you that what are the sort of questions that you will come across. What are the type of field that you have to solve question for. So I have already categorized everything. So the first is called UTF, which means uniform and transverse field. So the external field will be uniform throughout the space, and also it will be perpendicular to the velocity projection direction. Okay. So the direction in which you are projecting the charge particle and the magnetic field will be mutually perpendicular. So that's called the transverse field. So what is the meaning of transverse field here? That is velocity of projection is perpendicular to B. Okay. So the next will be very logically. So it is non-uniform but transverse. So now the next is obvious. So we are keeping the direction intact. It is still transverse. And the velocity of projection is still right angle to the B. But the B itself is varying over the space. And the best example is infinitely long current carrying wire. So if we have infinitely long current carrying wire, we know that the field will decrease as you go away from the wire itself, right?
Yes, sir.
The third category is the field is uniform but non-transverse. So the direction, I mean, the value is not changing, but it is non-transverse. So uniform but non-transverse. Okay. So that is a very interesting. And the fourth you make what? Neither uniform so non-uniform and a non-transverse field. I mean, that's very bad short form. Non-uniform and non-transverse as well, which is not part of our syllabus. And the reason is it's very difficult to study such motion when the field is neither uniform or nor direction is fixed. Okay. The fifth variety that you have to study in this chapter is called when uniform E and B are present. And there is a two subcategory when E will be parallel to B, it's given to you that E is parallel to B and the E will be perpendicular to B. And with this all five variation, you will be able to cover the entire chapter. Okay. The next part will be the torque analysis. So torque analysis, and the last will be the energy analysis. Here I will introduce something called the magnetic pressure or magnetostatic pressure, just like electrostatic pressure.
Yes.
And I can say ETC. So this is the like overall thing that we are going to learn in this chapter. So we'll start one by one. So before we start, we'll try to understand what is the the force and what is the meaning of magnetic force. So we'll start with the frame of reference again. So let's say we have two frame. One is the S, which is the ground frame at rest, and the other frame I will call S dash, which is moving with some velocity. So I'll call S as ground frame at rest, and this is the inertial frame. So let's say if there is an electric field in a frame of value E and B, if you observe the same from the frame which is moving, the answer will change to E dash and B dash. So as the frame will change, the field will get transformed, and the change of value of field in a different inertial frame is given by something called Lorentz transformation. And the Lorentz transformation is the byproduct of the Einstein theory of relativity.
Yes.
So the electric field and the magnetic field are not distinct field, rather they are frame dependent field. The only field which exists in nature is called electromagnetic field, and we say E and B are its component. Okay. So we can say electric and magnetic field. Electric field and magnetic field are component of a single field called electromagnetic field. Okay. Therefore, the electric force and magnetic force, the electric force and the magnetic force will vary from frame to frame, from one inertial will vary from one inertial frame to another inertial frame. But But the sum of the force, the sum of the electric and the magnetic force together remains same in all inertial frame and this force is called Lorentz force. So Lorentz force is basically summation of electric and magnetic force taken together, and each component, you can say the electromagnetic force will manifest differently in different frame. In some frame, one may be absent, other may be present, and vice versa. In some other frame, both may be present, but they are with a different value. So they are free to change independently each value, but the summation cannot change. So the sum of the electric force and the magnetic force is always going to be same. And because they are always going to be same, it means the Lorentz force is a constant quantity, and this quantity is free from the nature of inertial frame. Of course, we cannot go to non-inertial frame and talk about the electromagnetism because in the non-inertial frame, what we talk about is called radiation. So as we move from the accelerating frame, from the uniform velocity to the acceleration, the charge starts emitting radiation, and every charge will act as an antenna. So they will be the capable of radiating electromagnetic waves into the space, which is like a energy released in form of electric field. Okay. So oscillating charge does this, and of course, the source which will keep the charge oscillating will always lose energy, because if someone is, let's say, if you're driving a car and suddenly you stop, so all of the kinetic energy of the car is lost, isn't it?
Yes, sir.
And then you come back. So again, the source will provide you energy to come back. But when you lose some energy, it will be dissipated in some form. So here, of course, we cannot talk about the friction and the energy loss related to friction. So what we talk about is that the loss in energy actually appear as the electromagnetic radiation, or you can say radiation energy. And that is how the radiation is generated from the oscillating object. And therefore, the frequency of oscillation of the charged particle will decide the frequency of the wave emitted. Okay.
Yes.
And the frequency of the electric and magnetic field of the EM wave, when it goes to the other end, which we call the receiver end, the same frequency is interpreted and we create the same frequency current, and that is how we regenerate the signal on the other end. So it is like we read the frequency at transmitter, we read the frequency at a receiver, and we regenerate the signal in the machine. So that is how the wireless communication take place. And the wireless communication is all about the oscillating, or you can say accelerating charge. And therefore, our chapter of electromagnetism is solely based on the inertial frame. We never dig up in the non-inertial world and try to see what happens. That is beyond the course of JEE and also beyond my scope of learning. I mean, I haven't studied a lot about those things. I have very faint idea about the accelerating physics. So now, so the electric field in a moving frame is written as electric frame in the frame at rest plus velocity of frame into B into gamma. So generally we put gamma.
Are you like revising everything that we had studied in the first class?
Yeah, right. Do you remember?
Yes, sir.
Okay, so we'll just come back to the same point. And gamma we write as 1 upon 1 minus v square by c square.
Yes, sir.
So for non-relativistic speed, when the speed is not very high, we have a simplified relation. If v is much less than c, we say gamma is roughly equal to 1, and therefore it is good to write E dash simply as E plus. Now what we need to remember that v represents the velocity of frame. It is not of the charge particle. It's a frame dependent answer, right?
Yes, sir.
And similarly, the b dash we can write as b minus v cross E upon c square. Okay.
Yes, sir.
So because we are aware of the electrostatic force, and so what we are trying to understand is, let's say we have a source generating the magnetic field B. Okay. So this is the B in the ground frame, right?
Yes, sir.
And there is no electric field right now. So E is 0. Okay, this is S. So what I do is I try to choose another frame in which B becomes 0. So let's say in this frame, B is 0. In fact, the B dash is 0. The moment you try to make B dash 0, the E dash will appear. Now, of course, you're not trying to actually bring it, but it is going to appear for sure. So if you try to make one of the field 0, the other field will appear. That's very interesting. And the E dash, we can write as what? What is E dash? So the E dash will be the E present in the actual frame, which is nothing, plus V of the frame into B of that frame. Correct?
Yes, sir.
So I can choose a suitable value of velocity which can make this possible, and this is obvious from here. So if I make B dash 0, you can see this implies the B equals to V cross E by C square. So basically I can have the option of choosing V, which can actually make the B dash 0 in the frame. And therefore, once B dash is 0, this is the relation that we are going to have. But E dash will come into picture. Because if you make B dash 0, you cannot make E dash 0. You cannot make both 0 because it is the violation of force, right? Lorentz force. In
Yes, sir.
different frame, component will change. If one will change, other will change to compensate. So Lorentz force is an intact quantity. It's a constant quantity. So I can choose a frame in which I can make one of the values 0, but other value will pop up. And then the benefit is, what is the benefit? The benefit is that this frame, and let's say we have a charge here, it's just required now. So if we have a charge here kept at rest, this is a charge at rest. Now, if a
Yes,
charge is at rest, electric force is how much?
So
0.
0.
There is no electric force. Okay.
Yes, sir.
But now what will happen? In the frame that we have chosen, the Q will have velocity in the opposite direction, right?
Yes, sir.
Minus V. So if V vector is the velocity of frame, what is the frame velocity of charge? Minus V.
Minus. Yes, sir.
Isn't it? So what we can say that the answer for the force on a charged particle in S dash frame. So in S dash, the force on a charged particle will be Q into E dash, isn't it? U into E dash, correct? Because in that frame, according to S dash, there is no magnetic field.
Yes, sir.
And because there is no magnetic field, so there is no question of magnetic force. So the only force that it can experience is electric force, which is Q into E dash. And the E dash is how much? You can see E dash is V cross B.
Cross. Yes, sir. Sir, I don't understand the second statement that you had written.
Which one? This one.
So B, sir, if B dash is equal to 0, then B is equal to.
From this I derive from here actually.
Yes, sir. Sir, but then E is also 0.
Also 0, yeah. So that's why the B dash becomes 0. The B becomes 0 only.
But how's that? I mean, we had actually considered some value for B.
We are making B dash 0. If E is absent, then the B will remain unchanged. That's the meaning. Okay. No, so this will be B only. B dash equals to if E is 0. Just do other way around. Let's say we have a charge. Yeah, that's the right question. Let me just think about it. Okay. If electric field is 0, then in every frame the B remains same. B will not change. That's correct. So B will only change due to gamma, but gamma is almost 1. So we can say there is a slight change in B, but that is almost negligible, right? Okay, that's correct. So this will be, this we cannot write. Okay, we are trying to make B dash 0. Okay, so what I can say is that, okay, let's make E in, okay, let's make it the E also. Now this is possible, I think. In the first frame, let's say we have both E, B and E, right?
Yes, sir.
Yeah, now we can say, if we have both, then we can say for some velocity, the B may be 0, right? The B dash may be 0.
Yes, sir.
And that is only possible when the B and E will have this relationship. Okay. So when B dash is 0, then the B must be having this relationship, V cross E by C square. Okay, where E is the electric field or electric force.
Yes, sir.
Or we can do like this also.
Sir, can you just come back in a minute? I'll just take my laptop charger and come.
Sure. Oh, Josh.
Sir.
The class is still running, so can you join after 30 minutes?
3.5 को।
हाँ।
ओके सर, ठीक है।
Sir?
Yes.
Yes, sir.
So now, okay, I was thinking of different lists. Let's say if we have if we have E and B here, then what will be here? We will have E dash and B dash. If the frame is having some velocity, right?
Yes, sir.
And we have the formula written already, E dash and B dash. So for any charged particle, okay, I want to make B dash 0. So what I'm trying to do is I'm trying to make B dash 0. So in a frame, I'm choosing a frame in which the B should not exist. Okay. I want only E to exist. Okay. So for B dash to be 0, this implies the B must be equal to V cross E upon C square. So this is correct, right? Because we have E and B. So this relation is possible, right?
Yes, sir.
And if I take the mutually perpendicular direction, let's say if I choose E in a way, which is like X step and I step, we can actually achieve this easily. But nevertheless, let's keep it up to here only. The next step is when you make B dash 0, you have only E dash. And therefore, if I have any charge Q here, so we can easily write the force. The force on a charge Q will be how much? Q into E dash in the frame, right?
Yes, sir.
I can say in S dash frame, because the observer believe that there is only one charge Q. Okay. And what I'll do is I'll make this charge here, because if I put the charge there, it's going to move. So let's keep the charge here. So charge is kept in which field? In which frame? Charge is kept in the S dash frame.
Yes, sir.
So for S dash observer, the charge is at rest.
Yes, sir.
For S, the charge is in motion, isn't it?
Yes.
But luckily, since the charge is at rest and electric field is present, so force on the charge will be Q into E dash. Okay.
Yes.
And what is Q into E dash? What is E dash, by the way? So E dash is E plus V cross B.
Where is that?
Yeah, so we can write the force equals to Q into. So, okay, if I make E equals to 0, the problem is if I make E equals to 0, the E dash will be still, but for that we need B then. I cannot make B 0, I can make B dash 0. Ah, no, I got it. No, I got it. B dash is B. Ah, correct. Look at this. No, this is fine. Now I realize what was the mistake. Okay, here what we are going to do is we are not going to make B dash 0. Here we are going to make E equals to 0. So if E is 0, the B dash will be equals to B only, correct?
Yes,
And
sir.
E dash will be equals to how much? V cross B.
Yes, sir.
And because the charge is kept in the frame S dash, so the charge is at rest.
Yes, sir.
And because the charge is at rest, can we say there is no magnetic force? Because
Yes,
the
sir.
magnetic force is due to the moving charge, but a charge at rest only experiences electrostatic force. And therefore, the answer will become, now you can understand why the answer is the answer where we have. So now the answer will become if force on a Q equals to Q into E dash, but E dash is how much?
Cross B.
And because I can say, because this force is we derive as an electrostatic force, but in some other frame, this will act as a magnetic force. Why? Because the E is absent, right?
Yes, sir.
Because E is absent, so in ground frame, can we have electric force? No.
No, sir.
Here we have the electric force is 0. So the only force possible is magnetic force. And therefore, what
Yes,
we did was we throw the charge with some velocity V. Okay. Now, because the charge is moving with V and the frame is also moving with V, in the frame, the charge is at rest.
yes, sir.
In a way, if we attach a frame along with the charge will appear at rest, and therefore it will not experience the magnetic force. The only force it can experience is electric, and electric force itself is giving you the answer like this. So this is called the basically this force must be the magnetic force in the ground frame, isn't it?
Yes, sir.
And in the ground frame, you can clearly see the charge in motion will experience the force due to the magnetic field present, and the force is given by F equals to Q into V cross B. Understood?
Yes, sir.
Okay. So what is happening is, let's say if you have a current carrying wire. So this is the formula of magnetic force. And what V represents here, so if you try to understand V, the V represents the velocity of the charged particle with respect to frame in which the B is static. The B is constant. Okay. So the B value in the ground frame is static, it is fixed. Okay. As you move, the B will change, right?
Yes, sir.
So the V is not the velocity of charge only, V is the velocity of charge with respect to the frame of field itself. So here, if you want to write in this chapter, the way to think is, don't take V as the velocity of charge in the ground frame, take the velocity of charge in the frame of field. So think as velocity of charge think as velocity of charge with with respect to magnetic field, which means how the magnetic field will feel about velocity, what field will see the velocity, that will decide the magnetic force, and that is the formula which we need to interpret. Okay.
So then won't it be zero here in the S dash frame?
In the S dash frame, it is yeah. In the S dash there is no magnetic field, correct? But in the S dash we have electric force, which is same as the in the S frame, right?
Yes, sir.
It is like, see, the E dash will behave as V cross B. So in a way, they will transform one into other. So the net answer will not never change.
Yes, sir.
So here, the force possible is, here the Lorentz force is only magnetic force.
We interpret it as because of magnetic field.
Correct. Because here, yeah, here E is 0, B is non-zero.
Yes, sir.
And in this case, the Lorentz force is only due to the electric force, because the B dash cannot apply force on a rest charge.
Yes, sir.
So I have chosen a frame which is moving along with the charge. So therefore, it is at rest, and because it is at rest, so it is not eligible to experience the magnetic force. It will only experience the electric force. Okay, so there is a very famous question. Let's say, if we have a current carrying wire, so current carrying wire is like a moving charge, right? So it will create magnetic field. We know all about this, right?
Yes, sir.
So we know that if I choose a frame at rest, so it will only experience, the frame at rest will only see the B. Why? Because a charge, sorry, a wire which is carrying current is assumed to be neutral, because the positive and negative charge will be same, right?
Yes, sir.
So a frame at rest will see the wire as a neutral, and the only field present is B, and we know it will create a cross field. So let's say you throw a charge particle Q with a velocity V. So a charge moving in the direction will get attracted towards the wire due to the magnetic force, like this. So this is the expected path of the plus charge, positive charge. Okay. So what we do is we try to create another frame S dash, and we believe that it is also moving with velocity V. Now in this frame, the charge particle will be at rest. Correct. So the same, the velocity of Q with respect to S dash is 0. So technically, even though the B was present in the frame S, because the charge is at rest, then there is no question of force on a charge particle due to the magnetic field. Okay. So here, just because the frame is moving along with the charge, will it stop going towards the wire? The answer is no. Just because you change your frame doesn't mean I will change what I was doing earlier, right?
Yes, sir.
So what exactly happens in the new frame? So the answer is, in the new frame, the wire that you will see, just here, this wire will become actually negatively charged. That's very interesting. And because the wire becomes negatively charged, the force that the charge will experience is electrostatic force. So let's say at some time t, if the charge is here, moving with velocity v, of course it will not experience magnetic force, but this negatively charged wire will create the electric force, and this will pull it towards the wire, which means a wire which is neutral in S frame, the same wire will become charged in other frame. And this happens due to the theory of relativity. So in in theory of relativity, so first of all, I'll mention here. the neutral wire in ground frame will appear as the neutral wire in ground frame will appear as a charged wire in S dash frame due to a relativistic phenomena called length contraction. Okay. So there is something called length contraction. And what is length contraction? So if we have a rod, so let's say we have a frame S and we have frame S dash again. And this is moving with velocity V along the x-axis, let's say. And you have a rod kept like this. So let's say the length of the rod in the frame, this is the true length, let's call L naught. So any observer, if the observer will see the rod at rest, then what he will see is called the true length or the actual length. So observer in S dash will see the true length, which is L naught. But this observer will see the same rod as L dash. I mean, this observer cannot see the actual length, and that is the problem. Okay. So for a frame at rest, if you see a moving rod, okay, then, and if the rod is kept along the velocity direction, now of course I am not keeping the rod at same V is changing in the V is moving in the X direction. So the rod must have the two components separated in X. If I keep the rod like this, nothing will happen. The rule is the rod must be parallel to the velocity direction. In such case, the coordinate of this end and this end as observed from the S will not be same. Rather, it will be less than L naught, and this phenomenon is called length contraction. So we say that L will be equals to L naught by gamma. So the new length will be the length which you, so a moving rod will appear shorter to the observer at rest. A moving rod will appear shorter to the observer at rest. Okay. And this is called length contraction, where gamma is 1 upon 1 minus V square by C square, and because it is 1 by gamma, so it will become 1 minus V square by C square. So in day-to-day life, you don't see object moving really fast, right? Do you see it? So V is very, very small compared to C. Therefore, in our life, we don't see. Okay. But it really matters for the other purpose. Okay. So when we observe the wavelength of light, so wavelength of light is doesn't appear same in all frame. Okay. Even the wavelength will appear different in different frame. So if the source is moving with some velocity, then its wavelength will shrink actually. Okay. Because of the same phenomena, the length contraction. So although small it may be, but this is sufficient to create a very tiny electric field which will, I mean, you can say, imitate the magnetic field. So basically magnetic field is very, very weak compared to electric. very small, and the ratio is it's 10 power minus 10 power minus 8 is the ratio. So it is 10 to the power minus 8 times the electric force generally. Now length contraction is very interesting because the previous case, if you go back to the previous case, so this is the current carrying wire, and we have a frame. Now our frame is S dash, which itself is moving with velocity v. Okay. And there is another frame S, as we discussed earlier. Now for S dash, for this observer, if I just take any small piece of wire, now this piece of wire is at rest in which frame? Now this piece of wire is at rest in S frame, but in the S dash frame, the piece of wire will move backward, downward, right?
Yes, sir.
So in S dash, this looks like it's going downward because the wire, the segment is moving. For S dash, will it appear of same length or less length?
So it will keep decreasing.
Yeah, it will shrink actually. So for if S dash will look in front of the wire, it will appear shorter than its actual length.
Yes, sir.
Okay, so for this observer, the positive charge. Okay, now we can, just to make this simple, we'll assume the current is nothing but the flow of positive charge. It's all positive, and therefore the lattice becomes negatively charged, right?
Yes, sir.
So we have negative lattice points, and the positive electron is, like you can imagine, positive electron is a positive charge which is spread uniformly. Assume the electron is positive and the current is positive, so positive flow is there and negative lattice is fixed. So I will assume the drift velocity equals to v, just to make it simple. Now if the current, if the, you can say, if the current itself is moving with velocity v, then can we say the positive charge appear at rest in S dash frame? The positive charge will appear
Yes,
at rest. Okay.
Yes, sir.
So if I take the same length of positive charge, it will remain same.
Yes, sir.
Now the negative charge will shrink actually, or you can say it will, the negative charge will appear more compact. So as a result, what will happen, because it is going to be more compact, so more charge you can assume to be filled in the same one, right?
Yes, sir.
So when you see in the S dash frame, the overall charge in the conductor of length dl, the overall charge will appear to be negative. Now the same length will not compensate. Do you realize this? The same length will not compensate
Yes, sir.
because the negative charge is more compact, more denser, and the positive charge is less denser. So we say that the density of negative charge and the density of positive charge, the negative will exceed the positive, and therefore the same length of the wire will appear to be charged wire, and you can see it's negatively charged, as I discussed. So in S dash, the wire will appear negatively charged, and therefore the charge which is moving with velocity v, this will attract because of the electrostatic force. It is not the magnetic force, isn't it?
Yes, sir.
And that is why we say that, see, this is a very hypothetical scene in which I have taken the drift velocity as equals to v. If it is not equal, then in every case, every wire will have some surface charge density, no matter what. So we do not have the perfectly neutral wire. We always have the charged wire, but the charge which appears on the surface is very small because of the observer is moving at a non-relativistic velocity. And it is so small that in most of the scenario, such assumptions are ignored. We don't assume any charge. So depending on the context, we simply ignore it. So what I was trying to prove here that current carrying wire will exert magnetic force in a ground frame, that is the frame in which the B is constant. The wire is constant, of course, the wire is not moving. But the same wire will appear a charge wire also in some other inertial frame, which is moving. Okay. So this is the entire philosophy of frame of reference and how the frame converts one field into another field, and the way we observe the thing changes, but the sum, well, the Lorentz force, which is the basis of entire discussion, the Lorentz force remains constant. Okay.
Yes.
So with this discussion, I'll end today's lecture. I have just lecture after 5 minutes, actually. And we'll continue the force calculation in the next lecture. Next lecture, we'll be able to finish most of it. So in 2 lectures, this chapter will be over. So we can finish mostly in August or first week of September completely this magnetism. Hopefully, in by the month of September, we should be able to finish EMI and AC. And after that, September, we are done with most of the club. Then we'll start the modern physics and a revision of the 11th topic after that. Okay.
Yes.
In
Sir,
that way,
actually, in the 3rd week of September, I'm having my physics half-yearly exam.
no problem. You can take a break.
No, sir. Sir, the AC current, till AC current, the chapters are there, sir.
So what I'll do is I'll share a lecture. You can just watch it. It's very simple to understand. Okay. It's just 2-3 lectures.
Okay, sir.
If we can finish, I will try to finish. Okay.
Yes, sir.
Yeah. So in case if it is not finished, you can just watch and we'll again revise later on. Not an issue.
Okay, sir.
Okay. Bye and take care.
Bye, sir. Thank you, sir.